So hello, everyone. My name is Marco Cecconi. I am a developer in the core Q&A team at Stack Overflow. Today's talk is going to be about performance and architecture. It's an interesting talk, and it's similar to a talk I gave here maybe 3 or 4 years ago, in which I explained more or less how we architect Stack Overflow. In this new version, there's going to be a lot of talk about how we get to such results, and hopefully that will give you some good ideas on how to do it in your own company or in your own time. So first of all, what is architecture? So architecture, of course, is not something that was born with computers. Is something that has been with us for at least 2,000 years, is the art or science of building, and specifically building habitable structures. It has been described in writing for the first time somewhere around the 1st century DC. It hangs around 3 important concepts. The first one is durability. So if you build a house or a temple, you don't really want it to crash on your head. And if you build a website or build an application, you don't want it to crash at all. The second concept is utility. So it must be worth something, it must be doing something, right? So you build a house, you need to be able to sleep in it and maybe go to the toilet. And the doors need to be there, but you need to also be able to open it. You can't build a wall next to a door. And we all know that if you write an application, you want to make sure the application works and does what it is intended to do. What I find most interesting is the last characteristics, which is beauty. So it's important that when you build an architecture, this building that you're going to create is beautiful, is at an aesthetic sense. So how do we translate that into a website or an application? Well, of course, it's an aesthetic choice, so it's really up to you. In our case, we chose performance, and we consider that our own aesthetic quality. Performant code is beautiful code. So the first thing you need to ask yourself, if you're architecting, or if you go to an architect and you say, okay, can you build me a church? He's going to ask you, the first thing he's going to ask you, so do you mean this, right, or you mean this? And it's very important to understand what you're trying to build and what you mean exactly. What's your audience? How big is your application? Who's going to use it? What are your circumstances? These are the important things to understand. But we were talking about performance. So what is performance? Amazingly, the word performance has a really crappy definition. And if you look it up, it's going to say ability to perform, which doesn't mean anything, and perform means to do something. But I find efficiency to be very similar in meaning, and it's much more interesting. So efficiency is the ability to do something without waste. And a very good example of a method that lets us build theories and lets us build models that work very well without waste is the scientific method. I assume you all know more or less what it is. And I would like you to concentrate a little bit on the 3 purple arrows over there. As you can see, there is this small inner circle of 3 actions or 3 activities which work in a circle. So what you do is you make a prediction, you gather data, and you analyze the data. And then you act on it to do better predictions. So you create a model or you build something, you measure it, and then you analyze. And This is exactly what we do at Stack Overflow, and this is exactly how do you build something with high performance. So you build, you measure and analyze, and then based on your analysis, you can start building again, and so on and so on. So what kind of results can you get with this methodology? I think you can get pretty good results. So I was saying, I started giving this talk around 2013. And in 2013, there were around maybe 100, more or less 100 websites in the Stack Exchange network. Nowadays, 2016, we are 160. So it's a growth of about 50%. In terms of page views, we were around 400 million page views per month. Nowadays, we are more or less twice as much as that. So 800 million page views per month. So what's interesting is our server infrastructure. As you can see, it's flat. So everything else is growing, but our server infrastructure has not grown. And if you look better, you will see that we use 9 web servers to power 800 million page views per month. It's a lot of work. So this is not magic, and is a result of this methodology. By the way, if you look at Stack Overflow or the Stack Exchange network in the US, it does around 39 million unique visitors a month, which puts it straight between Wikipedia and PayPal, and number 17, 18 in the world for size on 9 web servers. By the way, so completely unrelated or related, you should trust all this quantcast stuff, not too much. Yeah, don't be a bit careful when you see measurements and grandiose claims of numbers. So I don't know if you're aware of this thing that happened. How many people know about it? About half. So for the other half, what happened is that North Korea screwed up their configuration of their own firewall or routers. And basically, it's allowed people to see how many sites are registered in their top-level domain, and there are only 28. Okay, so they're minuscule internet, and you can imagine them looking them like this, right? Hey, look at those pictures of cats. But if you were to trust Quantcast, they would not be looking at cats, but they would be looking at Stack Overflow. Because according to Quantcast in North Korea, we are number 1, number 2, number 4, number 6, number 9. And Stack Overflow wins with 244 uniques per month. Wow. So I don't know, not very trustworthy in my opinion. Anyway, so we were saying, build, measure, and analyze. And you're going to see a lot of these things, a lot of examples, and they tell you exactly how to do this. It's not that complicated, but it's very, very powerful. The only thing you need is your will. Okay, so let's talk about servers. This is a picture of a server room. As I was saying, there are 9 web servers, and there are 3 racks. There are very, very few databases, very, very few accessory servers. So you can take a small picture like this one, and that's the whole data center that serves Stack Overflow. Very small. So this is what we build, right? So there's actually someone, so we don't use Azure, we don't use cloud, we don't use a hosting company. There are Stack Overflow people, our SREs that actually physically go in here, build these computers, and put them in the racks. But then, once we have them, we have the tools to actually measure their performance. So this is a dashboard that we use, one of the dashboards. It's called Observer, and you can download it and use it for free. It's open source. Anyways, so as you can see, we have 9 web servers running, and they run around 5% load. So basically, we can lose all of them, apart from one, and we can still serve the pages. SQL Server, we got 4. 2 of these are read-only, and we use them for maybe just displaying the pages. The other 2 are read-write. And only a pair is serving Stack Overflow. The other pair is serving the other 160 sites. What's interesting in there is that the SQL Server machines, they are very, very beefy machines, of course. The Stack Overflow one, which is New York SQL 03 and New York SQL 04, has what? 768 gigs of RAM. It's pretty big. And the web servers are much smaller machines. They have 64 gigs of RAM. And it's a lot. We do a lot of caching. But I can assure you these machines are not particularly powerful. After that, we analyze. We see the data. We see the statistics. We measure how much the tables are growing. When do we need to change our machines? Do we need to add new storage, for example? We made predictions. And based on that, we build again. Okay? So this is a very simple example. So this example is interesting because everybody can understand it. I think every company that has some form of self-hosting environment that does something like this. But what's interesting in here was just to explain the cycle and to also point out a different thing. In this particular case, this cycle takes 1 or 2 years. So we refresh the hardware maybe once a year, twice a year, every 2 years and so on, depending on what we need. But it's a very, very slow cycle. What's very important is not only going around this cycle, but it's very important also to think about how many times you go through it. And every time you iterate, you can improve a little bit. So the faster you iterate, the faster you can improve. And so it's important also to consider the speed of each of these circles. So to give you another example, oh, by the way, sorry, before I forget, this is what the physical architecture looks like. There are routers and network cores. So we have basically 2 load balancer, the purple ones, based on CentOS and our HA proxy. Only 1 is active. We have the 9 web servers running IIS and Windows in the web tier. We have the 4 databases, of course. Then we have a lot of caching and a small pub/sub system. Well, not a small pub/sub system that we use for updating your pages in real time while they're on the screen. And we use Elasticsearch, and it's a small cluster of 3 machines. And then we have the service tier, which is still based on IIS, and what it does is does a bunch of things, but most importantly, it is an index of our questions by tag. So a lot of our lists of questions, if you navigate the site and you want to see all the newest questions or the recently updated questions or questions with bounties and so on, there are big lists and big queries on millions and millions of rows. In order to make it faster and faster and faster, SQL was not enough. So we started hacking SQL, and we started using full text search in order to make it faster. It worked for a bit. Then we need to make it faster again, and we created an index in memory on the web servers of, an index of the tags and the questions. And that wasn't fast enough. And then we split it off in this system. So basically, there are 3 dedicated servers that only do this and index questions by tags, and they can do very complicated queries. So you can ask them, okay, give me all the JavaScript queries, but not the jQuery queries. So it supports these Boolean searches as well. What's interesting is that we are pushing this even more. So right now, the version that we have until maybe this summer used to run typically a query in 100 milliseconds. The version that we have today, we have completely rewritten it, and it runs in very few milliseconds, like less than 10. And we are pushing for a new version based on CUDA and running on graphic cards and being massively parallel, which would run in about less than a millisecond. So really, really fast stuff. Again, how do we do this? We measure the performance. We see where the bottlenecks are, we analyze, and then we go and optimize the code where it's broken. And we do this all the time. So we were saying build, measure, analyze. Another example is another stuff that we build is code. So this is an example of code that I've shown a million times, but it's code that retrieves a set of posts that make up our help pages. It's not very important what it does. What's more important is how it does it. And as you can see in it, we use a lot of stuff which is not by the book. We break a lot of rules in this 10 lines of code. We use a lot of static stuff, which is really bad because you can't really do any dependency injection on it. And there is caching, and then there is SQL directly in the class that in the model that contains all the data, which is something that you should not do normally, right? So normally you would have a repository pattern so you can decouple it and you can write unit tests that don't depend on SQL. But hey, our SQL is literally in line in the method, so there are no layers. So it's a complete monoblock, monolith. So we write code. So what's good about this, though? There are many things which are good about this style of coding. The first thing is that it's fast, of course. But the second thing is also it's fast to write. So this thing takes very little time to write. Writing 10 lines of code, I can assure you 10 takes much less time than writing 100 or 200. But then how do we measure it? So here is an example of how we measure it. So we have a tool called Mini Profiler, which is a tool which appears on every page that a developer sees and that runs in the background for a percentage of users. And what it does, it profiles all that happens in the generation of a page. So when I go on this page here, I can see what's generating less than 200 milliseconds. I don't know if that is good or bad. If you do web development, for us, it's really bad. So I want to see why. And I can see a breakdown of all the operations that are needed. And each one has got a timing, and I got a list of all the SQL queries that are executed, how long they took. Redis, which is basically caching. And if I access the tag engine, I would also get the timings for tag engine. So I can get a complete idea right here of what's gone wrong with that page. Which is, it helps you a lot when you have to go back to that code and fix it, and you know where to go. And then we also store this stuff inside the SQL database. So I could go online right now and query maybe all the last day of logs on the question page and see the timings. We don't store all those details because it would be too much data, but the principal ones we do. And this was a very good day, and I did it for a tweet. And so I can see that in blue, you can see the time it takes to render the first byte of any question page in a day. And that's the distribution of the requests. And you can see that most of them, or half of them, are below 10, 11 milliseconds. And you can see the double bump. So there's a bump between 0 and 1 milliseconds. And then there is a bump between 10 and 11 milliseconds. The one between 0 and 1 is when we actually hit the cache. And the other one is when we have to build the page. So it's super fast. In orange, you can see the time it takes to run the SQL queries. And most of them run literally between 2 and 3 milliseconds. And Redis is so fast, we can't even measure it. Another thing that is important when you do this kind of operations is not just see what's going well, but also what's going not so well. And you can see on the right that sometimes we have burps, I would call them, or questions that don't go too well. And you can see in most cases is something that has to do with Redis. It's probably some network, because we talk a lot to Redis. It takes a long time sometimes. So this is another example of a loop, right? So you build code, you measure what's going wrong, and then you can analyze the data, see them in perspective, and decide where to spend your time. You will notice that in order to complete a cycle like this, it literally takes me minutes, right? I can write the code, which is terse, so maybe, I don't know, to write that is, what, 10 minutes? I can put it online, and putting something online for us takes around maybe 10 minutes, more or less. And measurement, it depends on how long you want to leave it, but you can get, at our numbers, you can get significant data in very, very short time, way less than a day. And so this cycle can be really fast. And this is very important, yeah? You have a fast optimization cycle. You don't waste time. It's not expensive. You do it, and you get faster. And the faster you get, the more you can do it. To give you an idea on how many production deployments we do, I actually measured it, because I'm talking about measuring all the time, and then I was just shooting numbers. But these are the actual number of deployments we did since I started giving this talk, more or less. So we were around maybe 3.5. So the blue line is the average per month, and the bars are the standard deviation. So it tells you how much we were close to that average in the month, and how many days maybe we were just doing crazy number of deployments. As you can see, we were around three deployments per day, and now we are maybe more around 4. It's slightly going up. As you can see, there is a huge bar a couple of months ago, and I'm wondering if any of you can guess what happened there. No one? What? We deployed a lot, yes, of course, yes. Or very little. Now, we deployed a lot. And we deployed a lot because we had a lot of bugs. And we had a lot of bugs because we deployed a new extension to Stack Overflow, which is called documentations. Are you familiar with documentation? Yeah? So only some of you? So documentation, so you all know Stack Overflow has to be a question and answer site. So you go and ask your questions, or you go answer questions, or just read. But we noticed that there were a few problems. Some of them is that most easy questions have been asked already. So unless there is a new language coming up, it's very, very hard for a new developer to come in and participate. Another thing is that not all topics are best expressed as a question and an answer. So what we did is we built this new system, which is in a way more similar to Wikipedia, in which people can put up documentation or even better examples of coding. So let's say you want to learn how to code in Prolog, for example. We have a topic called Prolog. You can go in there, and there are a bunch of subtopics like Hello World. So how do you write a Hello World program in Prolog? And you will find a bunch of examples. It's community edited. It allows a bunch of new people to participate. But of course, it's a whole new product that we pushed out. So the day we pushed it out, we called it Ride the Lightning, because there were hundreds and hundreds of bugs that we closed really, really quickly. So of course, that's a freak month. So this is the help center I was telling you about. It's a bunch of pages, and we need to cache them. And as you can see here, as I was telling you, the code is very, very terse. This is just a storage for the pages. It's all cached, is all in memory, and then is loaded from Redis if there is a cache miss, and there is ultimately loaded from database if we cannot find the event in Redis. So that's all that this does. It's very fast code. But talking about caching, we also use caching for more crazy stuff, because performance is not only about being fast when going to the DB, but it's also being fast in terms of not doing too many memory allocations. And if you can see this is a very popular answer. As you can see, it's got 4,000 upvotes. And the question is, if you're curious, is how do I parse HTML using a regular expression? And you don't, basically. Otherwise, you will go crazy and you start doing Zalgo. Anyway, so there is, on the top right, there are those tabs. Those tabs basically use a component. That component just encapsulates the links and encapsulates the labels. And we cache it. So this is the code that actually creates that top bar, as you can see. I hope you understand C# or Razor. It's probably easy enough. But basically what this does is it creates a list of 3 tab items. Each one of them only contains some text, some strings. So cheap to build and very small. But then it caches it. And it's interesting that it does this because probably going and checking the cache and getting stuff out of the cache takes more time than actually creating the object in the first place. So this kind of caching would actually probably slow us down on a superficial level. The problem is that this page does 90% of those 800 million page views. So we're talking about 720 million times per month that this code is run. And without caching, this would allocate about 3 billion objects. So that's a lot of work when you are not managing your own memory. So we're not doing C, right? C# as a garbage collector. A garbage collector is a background thread that is responsible for cleaning up all these objects that we innocently create every time. The more we create them, the more stuff he has to clean up behind the scenes. And it sounds like a ridiculous thing, like, oh, well, whatever, it's done really fast. Yes, but at these numbers, it's not so fast. It's a huge amount of garbage, and it's a huge problem. So why is that? So this is a very, very simplified view of how a garbage collector works. And you will hear more and more as many applications nowadays run on runtimes. JavaScript does that, and Java does that, .NET does that, and they all have a garbage collector, which can be, they're slightly different, they use slightly different strategies, but this part is pretty much always true. So basically, when you create an object, what happens? When you create an object, if you are in C, you're basically taking a chunk of memory and saying, okay, this chunk of memory is this object. When you don't need the object anymore, you explicitly tell the runtime to destroy that memory and mark it as available. So this is great, and it's fast, and it's a pain in the ass. Because you need to keep track of yourself when something is used and is not used, and there are so many bugs in C just because of this. Or you can use a garbage collector, which is a smart object or a smart background thread that does that for you. So you just create stuff like a crazy man, crazy person, and then when you don't need it, when you don't need this stuff anymore, this tool is smart enough to understand, hey, you don't need it anymore. I'm gonna release that memory so you can use it again for something else, which is great. Except there are 2 problems. One is there is this operation which is called garbage collection, which basically means that in background, this tool is trying to figure out which of your objects are in use and which of your objects are not in use. And how does it do that? Well, it has got some root objects which are always in use, and then all the pointers that these objects contain, mark the corresponding objects as alive. So he needs to go through all the possible objects that he has, figure out which ones are alive at any given time, and he marks all the rest as dead, and then he can clean up the memory. Of course, this is very slow if you have a lot of dead stuff around, or even if you have a lot of alive stuff around. And there is also the problem is that objects can keep other objects alive. Right, so let's say you have a tree of objects, of dependencies between objects, an object that contains an object, that contains an object, and so on. The complexity there is understanding that you need to navigate all this tree. So you can have many layers as a very recursive kind of pattern to understand all there is in there, and it can become extremely complicated. So normally you don't care about this. If you create enough garbage, you do care, because this basically, when it has to figure out what to clean, it stops everything. Right, so in Stack Overflow, what this does is you go on the site and you wait 20 seconds for a page. Because it goes, okay, wait a minute, let me see, I need to clean up memory. Because I cannot create any more memory unless I clean up some space. In order to clean up some space, I need to figure out, hey, these 800 million objects which I have in memory, which ones are in use or not. And that takes a lot of time. So another thing playing good with the garbage collector is a huge point, and is something that you may want to consider if you're starting to do performance work on this kind of interpreted, not interpreted language, but languages with a runtime like .NET or Java. Speaking of which, another thing that you may have noticed and may be wondering about, what does that _s thing do in this code? And I have another example here of an _s. So what this does is means, semantically speaking, instead of printing out this exact sentence, do two things. First of all, that dollar, short name dollar, it's a placeholder, replace it with the object I pass you. And the second thing is, instead of writing in English, write in the current language, right? Because Stack Overflow now is in 4 or 5 languages, and we want to have one version of the code running. So how do we do this? So normally, the way this would be done, okay, there's the crazy slow version, which most CMS will have, is that you have a different version of this string for each language in the database. And when you need to create the page, you fetch the right one. You can use caching all you want. We are talking about fetching literally hundreds and hundreds of thousands of different strings. So it does not scale very well. The other way you can do it is, instead of using a DB, use resource files, which are the same in a way. The strings are stored inside some static files, and they're loaded when they're needed. Again, great if you have a small site, and if you have a small number of resources. With large number of resources, forget it. It's just too slow. Because when you load them, it's a dynamic load. And when you do a dynamic load of a string, what happens? You allocate an object. So what we did here is something a little bit crazy. We decided, okay, so what we ideally want is not to allocate any string. And in order to not allocate any string, when that code is compiled, it has an intermediate step that compiles it to this C#, which is really super ugly, but basically creates the page. And we modified the compiler so it would output code which is written like this. So as you can see, this is calling a function with that one generated ._s_d1 blah 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 blah. That function with a funky name is a function which is generated when we compile. It doesn't exist in the source code. And literally, this is the body of the function, and it contains the strings that need to be run, that need to be displayed. So as you can see, there is no dynamic loading of strings. All these strings, they are static strings. They are created and they are compiled, baked in the source code. So when you execute a request, all this stuff is literally inside the source code and compiled in. And the way we do this is by extending the compiler looks up the database at compile time, downloads all the strings, and just creates all these classes. And this is just to avoid writing them as dynamic strings to make it faster. Another additional thing, this is our build times. So how long does it take to put stuff in production? As you can see, we were around 5 minutes. And then around release 11,760, something happened. What happened there is that we brought on our own optimized compiler, which is like 50% faster. Other weird stuff that we do, okay, this is broken, fantastic. Other stuff that we do here, you can see it, but you can imagine. I think there is some problem with the internet connection. So what happens here is that, so all modern languages have two versions of a string. There is the normal string, which is the constant string, immutable string that you call a string. And then they have another object, which is generally called a string builder, something like that. I'm not sure how it's called in Java and so on, which is still a string, but it's a mutable one. Well, the implementation of the mutable one made Microsoft change at a certain point, and it actually allocated an extra object every time. Guess what? We couldn't use it anymore because it was creating too many instances. So we had to create a pool of mutable strings that we mutate all the time, and we use those in order to create dynamic strings. So other stuff, dependency injection. As I was saying, we don't do much. But just to give you an idea of what the dependency injection is, some people don't use it, is that instead of going to the DB, instead of depending on the code that you call to know exactly how to create, in this case, for example, an order, you use an object called a container. The container knows how to give you a repository, which is an object that whose job is to get you stuff from this abstracted thing, which is a repository, which is typically maybe the DB, maybe cache, maybe memory, whatever. The important thing is that this object can get you an order by ID. And so once you get this object from the container, you can invoke it, invoke the get method, and get your order from storage, whatever that is, which is great. Okay. Which is great because it allows you to do stuff like this, which you can see again, but it allows you to do stuff like, for example, instead of simply getting something from the DB, you can run through layers of security. You can run through login. You can run through caching. You can add all these sort of things just by configuring the container to give you a different thing. So let me see if I can refresh this and if it works better. Otherwise, we're going to be seeing a lot of these broken things. Anyway, so yeah, here we go. So probably now it's going to be better. So what's happening behind the scenes, though, is something like this, right? So at some point, if you want to have all these services in, you need to create some objects that implement them for you, and then you pass them along, typically in a chain, which each one depends on the next one. This, of course, creates a ton of problems for the garbage collector. So there are two things you can do here. You can either create them every time, and you create too many instances, or you create some singletons or long-lived classes, so you don't have to create them every time. But then you have a bunch of objects which sort of live long and depend on each other, which is another nightmare for the garbage collector because they become complex trees to navigate. So in either case, if you do these kind of things, you are going to hammer against garbage collector at some point. Okay, so this is going well. Wi-Fi is better now. Let me see. Yeah, Wi-Fi is terrible. It's down. Okay, so I mean, I don't really need the slides to go on. I just have 5 minutes anyways. All these kind of things, they might sound crazy, but they're not crazy when you measure everything and you know why you're doing them. For example, how do we know that we have all these problems with garbage collection? Actually, we know because we measure it. You know, there are performance pointers in Windows that tell you that. Another thing that I wanted to talk to you about, which is something which is almost like build, measure, and analyze, but not quite, but it's interesting, is how you build a team that can handle this kind of things. And the way you do it, again, you build hackers, you hire hackers or good developers, or people who are extremely passionate about what they do. And then you need to enable them, right? So you need to give them the tools they need. For example, I don't know, good computers. A lot of developers work on really old, 60-year-old computers that probably nobody would want to use. I've seen colleagues sometimes in my career bring out their own keyboard at work because the keyboard they have is like the $15 one. Once you give them good tools, and in general you enable them to be the kind of developers you hire them for, they will give you results, and they will give you performance code, and they will give you code which is also efficiently optimized. And this allows you to better use their time. So it's like you have more developers. You have just increased your capacity that way. So this is not the same thing, but it's a 3-step cycle. So in conclusion, there are 3 or 4 things that I really, really care about. The first thing is, if you want to build performance size, you need to understand that architecture is not only doing something that works, it's not only something that doesn't fall down, but it's also building something beautiful. And you can choose what you mean by performance. For us, it's raw speed. For someone can be, if you are building a banking system, that you never lose money. It's another form of performance. Then you use the scientific method, and in particular the 3-step method, to actually run cycles really, really fast and make changes really, really fast to your product. You need many, many cycles to get this kind of stuff. This allows you to build systems which are high performance, but also which are highly optimized to your particular problem. One example that I couldn't show you is that, how we work around not having tests, because we can't have tests with this kind of architecture, and we do it because we have developers as an audience. And our developers, when we put out a bug, they tell us there is a bug. They are our own automated testers, and they tell us a solution. But this is not something that you would design. It's not something that you would build because you say, okay, I'm crazy, I'm going to do that. It's something that you can see and it emerges through this process of adapting to reality. And finally, it's important that you hire the right people, and we have a great product, and that's how we monetize, actually, to help companies find the best people for their particular situation. And then that you use them at their best of the abilities, so they're happy and they're productive, and then, again, you need less people than you would think. Our team is much smaller than you would imagine. So, more or less, this concludes my talk. One last thing. We created a new badge. If any of you are Stack Overflow users, there is a new silver badge which was announced yesterday. And we give it to people that come see our talks or come interact with us. It's called Not a Robot because, you know, like a CAPTCHA, we know you're not robots if you come and talk to us. And if you want it, we are going to award it. You just need to give your data to our booth, which is over there where the games are. So thank you very much, and sorry again about the slides.